Hi everybody, we are going to learn about the metric or distance formula in Euclidean or flat space. Okay, so for the first thing, vocab, meter means to measure something. So an ammeter measures amps, voltmeter measures volts. A meter stick measures distance, and they just don't call it a distance meter. Okay, so in general, in math, a metric is the distance formula in any given space. The space you guys are used to is Euclidean spaces, which are flat spaces. In the course of this video homework, you're going to see some other examples of spaces, some curved spaces, and they're going to have different metrics, different distance formulas in those different spaces. The reason this is relevant is not just trivial. The reason this is relevant is because the universe actually doesn't have a perfectly flat space. The curvature of the universe is non-zero, and so you need to understand how the metric works in curved spaces if you really want to understand relativity. But before you do that, you start with a flat space. So if I have a 1D line here, then this is pretty straightforward. The distance formula here, the metric, is the absolute value of x2 minus x1. Okay, and I'm sticking these absolute value signs on here because the distance is always going to be positive. So in two dimensions, what we have here is two coordinates in two dimensions. We have an x and a y. And the way you want to think about this distance formula is imagine a square surrounding these 2 points, which I have drawn over here. So the way this works is anytime you are moving along the x-axis, the x value is going to be changing, but the other axes values will not, okay? Movement along the x-axis is independent of movement along any other axis. So as we move along the x-axis, we're going to change to x2 here, but our y value is going to remain unchanged. Similarly, if we move along the y-axis, our y value is going to change, but our x value is going to remain unchanged. So now if we look at the legs of each one of these, of this right triangle here, here we have x2 minus x1, just our one-dimensional distance formula. And this here is going to be y2 minus y1. Okay? And now putting this in terms of Pythagorean theorem, we are looking for the hypotenuse c. And so c is going to be equal to the square root of a squared plus b squared. And we know what a and b are in terms of our coordinates. So we are going to have x2 minus x1 squared plus y2 minus y1 squared. Note that the square root of anything is always a positive number. And so this distance is always going to come out positive. We don't need this absolute value sign here. Another simpler way of writing this formula, which will make this a little bit more intuitive, is we know x2 minus x1, that's our change in our x. Okay, so we're going to have change in x squared, and then this y2 minus y1, that is going to be our change in y. Sorry if this is hard to read here, but all this is saying is that this distance is the square root of this distance plus, or the square root of this distance squared plus this distance squared. Okay, I think a lot of you are probably comfortable with that. 3 dimensions, it gets a little bit more difficult. Now, in 3 dimensions, we have 3 coordinate points. Okay, so just like before, we imagined this as a square. This time, we're going to have to imagine it as the 3-dimensional version of a square, which would be a cube. Okay, so I've drawn my cube here, and what we have is all 3 coordinates are changing, x, y, and z, and I am looking for this distance from the front bottom left corner to the upper back right corner. The way you want to approach this is by thinking about what we talked about here. If you move along the x-axis, the x value changes, but the y value remains unchanged. Okay, be careful here because our axes are a little bit different than we're normal used to. In 3 dimensions, z is traditionally put up, x in this direction, y in this direction. So as we move along this direction, we're actually moving along the y-axis. I'll go ahead and put these axes here to make this easier to see. That should be z. Okay, so as we move along the y-axis, the y value changes, but the other 2 do not. So this point would be x1, y2, z2. So again, y changes, no other variable does. Then we're going to move along this axis. This is the x-axis. Notice how they're parallel. That means the x value is going to change to x2, but all of my other values will remain the same. The reason I'm doing this is because if I connect this point not to my final destination, but to an intermediate destination, this bottom right back corner here, what we see is we have a right triangle. So look at this right triangle here, and we can do Pythagorean theorem just like before to find this distance. Okay, if you notice, we are ignoring the z dimension right now, so this is going to be the same exact distance formula. This distance here is going to be the same distance as this c here. Okay, so I'm going to call this C1. You're going to see why in a second. So we're going to have C1 is equal to the change in x squared plus the change in y squared. But what I'm looking for here is this. Now what I want you to notice is we've created another right triangle here. We actually have another perpendicular angle in between our distance between the 2 points, the distance along the bottom of the box, and this vertical wall here. So if you notice, this is a right triangle going from one corner of the box to the other. What happens now is our final answer we want, I'm going to call this C2. And what we see now is that C1 is just another leg of this right triangle. This here is going to be the change in z. So this distance is the change in z. Now going to Pythagorean theorem, of course a squared plus b squared equals c squared. C1 is my a. My b is going to be the change in the z. And then my c is what I'm calling C2 in this case. So using the fact that I know what C1 is, if I plug this in here, then what I'm going to get is this. You notice the square root cancels the square here, so I'm going to get change in x squared plus change in y squared plus change in z squared is equal to C2 squared, and therefore, as my final answer, the distance between these 2 points is going to be the square root of x squared plus square root of y squared plus z squared. I said that wrong, but this is the correct formula right here. So I want you to notice how similar this looks to the formula we already found here. In 2 dimensions, with just x and y, the distance formula is the square root of each dimension squared. In 3 dimensions, we have the exact same result. We have the distance formula is equal to the square root of all 3 components squared. That's not a coincidence. We can expand this to higher dimensions. If I wanted to know, and I can't draw it, but if I wanted to know the distance between 2 points in a 4-dimensional space, then what I would have to do is I would have to imagine the 4-dimensional version of a cube, just like a cube is the 3-dimensional version of a square, which is the 2-dimensional version of a line. We would need to imagine a 4-dimensional version of a cube, which of course you can't do. But when you do that process, you're going to see it results in exactly the same, where we would have one more right triangle in our derivation process, and we would get that the distance formula in the 4th dimension, so the 4th dimensional Euclidean space metric, is equal to the square root of change in x squared plus change in y squared plus change in z squared plus whatever you decide to call that 4th dimension variable. Okay, have a nice day, you guys.